All right, everyone. I am here with Scott Clark. Scott is co-founder and CEO of SigOpt. SigOpt is a longtime friend of the podcast and a founding sponsor of our recent conference, TWIML AI Platforms. Scott, welcome to the TWIML Democast.
Thanks so much, Sam. I appreciate you having me.
Absolutely. So let's just jump right in. You not only are, not only are you such a great friend of the show, but you've been on the show. I think this is your third time on the podcast. And I think you are the first person to make it to 3. So welcome.
Always optimizing.
Exactly. So this is something new for us. We call it a democast, and it is an interview. We will be kind of going back and forth, but ultimately we will get to a demo. Will it be a live demo, Scott?
It will be a live demo with random data, so we'll see how well it goes.
All right. So, and it will not be too long before we jump into that demo, but before we do, refresh us on your background and what SigOpt is up to.
Yeah, so I'm co-founder and CEO of SigOpt. Studied a bunch of different optimization techniques in grad school, applied that in different settings in industry, culminating in writing some open source called the Metric Optimization Engine while I was at Yelp. And then about 5 years ago, I took some of what I learned from writing that open source, some of the needs I saw in the industry around having better ways to do experimentation and optimization for modeling, and founded SigOpt. And that's what we do today. We provide software tools that really enable modelers to augment their workflow, whatever it may be, to get the most out of the experimentation and optimization that goes into building good differentiated models.
You, as I mentioned, were a founding sponsor of the TWIML AI Platforms. Talk to us a little bit about where the company fits in the stack that enterprises are standing up to deliver models in production in scale, and why that whole idea of platforms is important to you.
Definitely. So what we're seeing is as firms start to invest more in differentiated modeling, where they're applying some domain expertise, context awareness, unique models, unique data, whatever it may be, they're wanting to really leverage the expertise they have in-house and are hiring in-house. And that requires customized tools in some areas. It requires flexibility in others. And the platforms that we're seeing built up at some of our customers, whether that's leading credit card firms, the world's largest streaming service, the US intelligence community, top algorithmic trading firms, et cetera, it's all about enabling that expert. And so we sit in the middle of these applied differentiated modeling platforms by allowing the user to do world-class experimentation and optimization on models, regardless of what those models are, regardless of what hardware they're being run on, and regardless of what the end application or starting data actually is. So we're seeing massive investments in a wide variety of different areas here. And our goal is to be this agnostic tool that sits in the middle that allows you to standardize on experimentation without constraining your experts in any other way.
Okay, and your presentation at the TWIML was focused on kind of your experiences or what your customers' experiences are, what you've learned from your customers' experience in terms of like how to put a platform together. And in particular, you had this really interesting, I thought, kind of take on buy versus build. And it wasn't like, do you buy versus build the platform? It's like, you're going to pull this thing together from multiple components. Where do you buy? And where do you build, and how do you make that decision? Can you give us a snapshot of the learnings that you brought to that presentation?
Definitely. So again, it's important to build where you have some edge over the rest of the world. And that could be expert knowledge, that could be bespoke requirements. That's something where you uniquely can attack the problem. And a lot of times for our customers, that lives at the data preparation, the ETL layer, high frequency or market making firms for our algorithmic trading customers look very different from mid frequency firms that look very different from a credit card fraud team, looks very different than a streaming service, et cetera. So there's a lot of unique requirements, needs, and application-specific expertise that goes into building a good data pipeline. At the back end of the system as well, deployment is another kind of very custom bespoke need that's very application specific. Whether, again, it's high frequency trading versus large streaming services versus fraud detection at the edge versus some sort of predictive maintenance. All of these have different needs, different requirements, different constraints, et cetera. So we often see a lot of firms building and applying those core custom requirements at the edge, but then at the beginning, the game flips, and it's all about flexibility. It's all about leveraging really robust and standardized open source, but understanding where there might be trade-offs in more academic approaches, where there may be trade-offs where you can take something off the shelf to help augment your experts without necessarily forcing them into a constraining box. So customization at the end, flexibility in the middle, and then really leveraging tools to make sure that those experts that are building those custom tools that in that flexible environment get the most out of them, utilize their compute as well as possible, utilize their domain expertise as well as possible, and ultimately get to the most performant and high impact models.
And so presumably that space is where the SigOpt tool fits.
Exactly. So we sit in the very middle of the stack here, as you can see in this slide, kind of between where you're going to be developing the actual code for models, these kind of differentiated, bespoke models where you're applying domain expertise, context awareness, et cetera. And we'll bolt on top and help you tune and experiment with all of the different configuration parameters and choices that go into making these models as performant as possible. Not touching the underlying data, agnostic to the end application and the hardware layer it's running on, but really making sure that you get the very best version of this model that accomplishes whatever you're trying to achieve.
Yeah, one of the things that I think about over the past, that's kind of characterized the past year to 2 years in this space is there's a lot more conversation about, things like auto ML, automating, data science, and, to some extent kind of automating hyperparameter tuning as well. So it's, unlike 3 years ago, it's something that is on our minds now. It's something that we're talking about. What do people need to be thinking about in this space and when they are, thinking about trying to drive some degree of automation into their model development and experimentation pipelines?
Definitely. So we've seen the rise of this over the last 5 years. I remember being kind of the heretic at NeurIPS and ICML yelling that you should tune your hyperparameters and your architectures and things like that. One thing that people have really realized over the course of the last 5 years, though, is a lot of the foundation and low-hanging fruit required just to produce models is now kind of coming into place. People are building these platforms, and they're looking for these additive boosts to those investments that they've already made. But there's a lot of things that go into making a good experimentation and optimization platform. A lot of trade-offs that we've learned by taking the state of the art from the academic literature, advancing it with our full-time research staff, but really building an enterprise solution to this problem as well to service our customers around the world with a diversity of needs. And that comes around making sure that this process is reproducible, that you can share the results, that you can collaborate, that you don't need to reinvent the wheel every single time you need to do experimentation. It comes to algorithmic efficiency. Instead of just taking a single path through the academic literature and pulling down open source that was written to do research, by taking our patented peer-reviewed approach to the problem, you can get results an order of magnitude or more faster, get better results out of this system. And when outcomes really matter, whether that's in algorithmic trading, whether that's in fraud detection, whether that's in a recommender system, every little bit that you can additively squeeze out of the model on top of the investments you've already made really matters. And then finally, we've made this massive investment into making sure that this is a reliable platform. Many firms with billion-dollar models in production rely on us in order to make sure that they get the best possible results. So this is about having a stable system that can really attack the full volume, variety, and complexity of their experimentation and optimization needs, with a full-time staff backing it up as well too. So it's shining light on this otherwise opaque problem, focusing on it and doing it extremely well with a best-in-class algorithmic solution, but also doing it with an enterprise focus to make sure you're not just taking an optimization problem and turning it into an optimizer problem, but you're taking an optimization problem and just solving it.
Mm-hmm. So you started out talking about reproducibility. A big aspect of that like automation is starting to gain more visibility in the industry. But then there's this whole kind of underbelly of that, which is the ML ops and like versioning your models and stuff like that. Is that something that you see your customers worrying about as well?
Definitely. What we've heard from a lot of different firms is when it comes to experimentation, oftentimes that's brushed under the rug on the tooling side. So it's things where people might be checking in code while they're developing a model, but then they'll go off and tune it or play with it or experiment with it. And more often than not, that might mean a brute force grid search or random search variants like hyperband. It might mean a manual search, trying to do high dimensional optimization in your head. But more often than not, it actually means only the best answers get checked in at the end. You end up with these config files with a bunch of magic numbers in them with no history of what was tried, why it was tried, insights gained along the way, different kind of iterations of experiments, etc.
Why do I need the history of all the bad things that I did?
So next time you come to that problem, what you should avoid, where you should start, how you can get to that best solution faster, or if you're in a regulated industry, so you can replay that experiment and say, this is exactly how I got to this learning rate, this number of estimators, this max depth of my trees or whatever it may be. And these are all the different metrics that I tracked. Here are the different trade-offs that I made. And ultimately, that can help a junior data scientist get up and running very quickly. But it can also make sure that a senior one can reproduce their work for the next project that they have.
And so is that history primarily for humans, whether regulators or the junior data scientists, or does the history the history of my, building and training a model A inform somehow the optimization of model B? Like, can the machines also use that history?
Definitely. So we have a handful of advanced features that we've developed over the last 5 years of doing really applied model experimentation and optimization. One of them is this concept of being able to transfer knowledge about similar tasks in order to bootstrap another tuning problem. So you could imagine if the data changes very slightly in a fraud detection setting or an algorithmic trading setting or whatever it may be, you might want to be able to bootstrap off of that prior information that you've gained in order to solve this new problem a little bit faster. So that can happen at the insight level with experts, and I'll show you what that looks like in the live demo. It could also potentially happen at that more automated level to make sure that, again, that wall clock time, that compute time is used as efficiently as possible. And a lot of that goes into that core optimization engine, which I have here is the middle pillar of our product suite, making sure, again, that for any of the applied optimization problems you have in the real world, we're taking the best of the academic literature, putting it behind a simple interface, but allowing you to solve your problems instead of having to become an expert in the research to even phrase them in a specific way.
Okay. Did someone say live demo?
Yep, coming up here in a second. It might be worth kind of going over the interaction diagram at a more visual level before I dive into the actual code. But basically, the way that SigOpt bolts on top of these underlying machine learning algorithms, algorithmic trading strategies, recommendation systems, self-driving car algorithms, whatever it may be, is by interacting at the configuration layer. So every machine learning algorithm, every deep learning algorithm, every reinforcement learning algorithm, every model has configuration parameters. You can call them hyperparameters, architecture parameters, feature embedding parameters, configuration parameters, whatever it may be. But what SigOpt does is it takes in all of the information about what you can tune about that system. It provides suggestions for what to try and evaluate. You report back some metric or set of metrics that you care about. We learn from that to suggest the next thing to try and repeat. And what we're doing is we're querying this underlying model of yours, trying different configurations, learning how well they perform, trading off exploration, learning more about that space, and exploitation, exploiting that knowledge to drive you to better and better results, to ultimately get you to that best configuration as efficiently as possible. And this can happen sequentially, it can happen in parallel, it can happen with single metrics or multiple metrics, small parameter spaces, large parameter spaces. But at the end of the day, the goal is just to bolt on top of whatever you have, from a simple XGBoost model and scikit-learn to an extremely complex neural network for a recommendation system or self-driving car task or whatever it may be, and help you get this additive boost on top of everything that you've done on the data side, the modeling side, and the evaluation side.
So basically, as a user, I need to tell the SigOpt tool how to optimize my model. I need to give it access to whatever parameters my model or my system cares about, and then SigOpt kind of does its thing and optimizes it and tells me what those optimal parameters are.
Yeah, you tell us all the knobs and levers you have. We'll tell you specific settings for those knobs and levers. You tell us how well they did. We'll give you new settings and repeat. And at the end, what you have is this optimal set of settings that then gets you to the most performant version of your model, however you define that.
And so in order to get to that, do I have to change my code? Am I wrapping it? I see REST API. Do I have to wrap my model in some kind of REST API, or are there different ways to go about it?
Great question. And I think that's a great segue into live code example. So what I'll do here is I'll run through a simple IPython notebook that I coded up right before this this interview based off of some work that some of our team did.
No
and
pressure.
Be able to, yeah, exactly. And what I'm going to do is I'm going to generate a synthetic data set, apply a standard classification algorithm to it, in this case, XGBoost. I'll show kind of why this is a difficult problem. I'll optimize it with SigOpt, and then show an extension of how we might go about this kind of iterative experimentation to ultimately drive to the best possible business outcome. So this is a fresh notebook here. So I'm going to load up a bunch of stuff in pandas and scikit-learn and matplotlib. I'm going to generate a synthetic data set using a handful of the synthetic data set creation tools that are available within scikit-learn around making Swiss rolls and Moons data sets and things like that. Basically what we have is that—
Is Swiss roll a technical term, or are we talking about like baked goods here? I've not seen that data set before.
It is a technical data set that looks like the baked goods. So you can imagine two different classes that kind of spiral into each other, where you wouldn't necessarily be able to make a good linear discriminant between them.
Got it.
So because you can't make
it just made me hungry.
This is delicious data here. What you can see here is this kind of spread of different data points. It might be hard to visually decide what makes sense. It's in 3 dimensions. How does yellow differ from green or teal or whatever it may be? And again, because there's not a great, like, obvious linear discriminant here, something like a linear classification or an SVM or something like that might not be a great example, but there is structure to this data. So what we're going to do is break it into a training and test data set, and we're just going to throw XGBoost at it. So using the softmax actual objective function in this case, since we have a multi-class classification problem.
Not a lot of customization here of the hyperparameters or—
Exactly. This is what happens when you have a data set and you take something off the shelf and you throw it at it. So imagine this is the AutoML solution. There are a bunch of hyperparameters in there, as you see when I kind of hover over this.
That's a bit of a raw stab at AutoML.
No, it makes a lot of sense when you need fast answers and you need commodity, just very quick, off-the-shelf answers. It doesn't make as much sense when your business depends on it and you need to differentiate yourself in some way and apply some domain expertise.
That may be true. I think, though, that AutoML might, if AutoML could respond, it would say it's not just default hyperparameters, it's a process that gets you to some kind of optimization that's better than default, right?
Yeah. So some of it's brute forcing parameter feature transformation. Some of it's brute forcing different algorithms. Some of it's brute forcing different hyperparameters.
Mm-hmm.
But at the end of the day, what we see for a lot of our customers is they need to apply something special to the data. Just random max min feature generation doesn't necessarily make sense to them. They might want to apply a very specific model to the problem, so an off-the-shelf method might not work. They might have very specific objective metrics beyond just academic ones like accuracy or whatever it may be. And so that's usually where we come into play for these more differentiated, higher value models that you would apply a machine learning engineer to as opposed to a business analyst.
Got it.
What we see here, though, is that XGBoost has a lot of tunable hyperparameters. So I have the default ones here for max depth, learning rate, number of estimators, call sample by tree, and med-child weight. What we saw was that the default set got 0.525. So if we were trying to do this by hand, trying to do 5-dimensional optimization by hand, we might do something like, oh, what happens when I change this to 200? Okay, that didn't have any effect at all. What happens when I change this to 1.15? Oh, that made it a little bit better. What happens when I change this to 0.9? It didn't have any effect. All right, going up didn't help, so maybe if I go down, okay, that made it worse. You can
Doesn't
see
it put
how
you in like the top 10% of the universe to only change one thing at a time and see what its impact is, as opposed to changing a bunch of stuff?
Yeah, so what you'll see is by doing it one at a time, we're not actually getting that much information. This might not be a locally convex problem. It's a 5-dimensional problem. None of this is being recorded. Maybe I'll stop here and say, hey, I did better than the defaults. I'm just going to check this into production. I tried it 6 times. What can you do? So this is where SigOpt comes in. So instead of doing it by hand, which we just saw, 5-dimensional optimization is very difficult to do by hand, even one parameter at a time. Instead of brute forcing this with something like a grid search, or even if I only looked at 10 parameters per dimension, that would be 100,000 different things I would have to try. We're going to try SigOpt's ensemble of Bayesian and global optimization techniques. So what we'll do is install SigOpt. Looks like we're already in Google Colab. I'm going to use this API token that I generated for this podcast, and I'm going to destroy immediately afterwards. And we're going to create an experiment. So first thing is we need some way to be able to evaluate different configurations that we want to attempt. So what we're going to do is we're going to take that XGBoost classifier, and instead of having constants here, we're going to allow SigOpt to modify them as we go. So you see we're modifying these 5 things. We didn't end up doing this one. And at the end of the day, it's just going to return the model, and then evaluating it will just return the accuracy. So within SigOpt, what we want to be able to do is basically—
So again, this is just going back to the previous conversation. These are the 2 things that you said we needed to do, like give you a way to manipulate the model parameters and tell you how we're doing with each step.
Exactly. So create model here is going to generate a model. That's this step here in the upper right. And then evaluate model, in this case, is going to just return an accuracy score. But this could be something more complex, like run through a back test of the equities market and return a Sharpe ratio. It could be evaluate a reinforcement learning algorithm through some synthetic test environment. It could be whatever it is that's actually what you're trying to achieve with this model. In this case, it's just returning accuracy, and that corresponds to just evaluating the model here. So we've generated synthetic data, we have a way to build a model, and we have a way to evaluate the model. So now we need to tell SigOpt what to train and go through this for loop.
Yeah, and you glossed over a couple of words that are pretty important, I believe, to the way you do this: Bayesian optimization. Give us an overview of that and how it differs from some of the other things that you mentioned. You mentioned grid search, random search is another strategy.
Definitely. Let me fire off this experiment, and while it's running, I expect it to only take a couple of minutes. I'll okay. Dive through that. Okay. So first, again, we want to define the space that we can search over. In this case, we're taking those 5 hyperparameters that I was manually tweaking before, and we're going to search over them. So some of them are continuous parameters, some of them are integer parameters. SigOpt can also handle categorical parameters. You can handle constraints or conditional parameters. Basically, any way you can define the problem that you're trying to tune. But these are the knobs and levers that we can set.
Mm-hmm. And just an observation, while this may look at first glance like setting up a grid, you're not giving a step. You're not.
Exactly.
You're just setting the bounds.
Exactly. So you're going to set the edges of what would be a grid, but instead of blindly searching through that in lockstep, we're going to learn from every parameter to decide what's the most intelligent next thing to sample. And that's really what Bayesian optimization does, is trading off exploration of that parameter space with exploitation of the knowledge that we already have to drive you to better and better performance instead of just blindly stepping along a grid or randomly just hoping you get lucky and throwing out all historical information you might have.
Got it.
For this specific experiment, I'm going to show what it means to have put in a baseline, because we already did the default here that got that 0.525 parameter. So might as well give that to SigOpt. We can leverage any historical information you already have about the model. If you've already run a grid yourself, already tuned and tweaked things, one of the joys of Bayesian optimization is we don't make a hard assumption that we came up with every suggestion ourselves. You can interleave us. You can bring your own optimizer. We play well with others. So in this case, we're going to set this baseline that we know we have to beat, because this is what happens when you just pull it off the shelf. And then we're going to go through this optimization feedback loop where we get a suggestion from SigOpt. We evaluate how well it did in that function we set up before. We tell SigOpt how well it did, and then repeat. So what I'll do is I'll kick that off. I'll jump over again here. We define the configuration space. We try something. We tell us how well it did, and repeat. What that looks like on our dashboard here is there's a fresh experiment, XGBoost examples. It has done 32 observations thus far. We've taken that 0.525. It was able to quickly get up to what I did by just kind of tooling around in one dimension. You can see it's already actually found a significantly better result here at 60% accuracy, something that I might not have naturally done by doing one at a time, because you see it's kind of modified a handful of different things here.
You wouldn't have set that learning rate out to 15 decimal places?
Exactly. And grid search would have also not done that as well. You probably would have aliased over the actual optima here. What we see here, though, is it's continuing to improve as it learns more about that space. It's finding regions that make more sense to sample. We can see in multiple dimensions what that looks like. We can see for this specific randomized data set, max depth and log learning rate tend to be the more important parameters. We can see that in certain cases, we might be brushing up against the edge of the parameter space. So you can see call sample by tree, all the good solutions are near 1. It's not a very important parameter because of that. It's a very obvious what you should do. So if I ran another experiment, maybe I would cut that one out. But at the end of the day, we've taken that model that it took me a little while to try to just play around with to get to 0.55% accuracy, and we got it to 0.65. We can see exactly what was tried. Here, we can manually add suggestions if we want to do a refined grid search or perturbation analysis after the fact. But at the end of the day, you could check into production. This was the configuration that got me the best result. Here's how I got there. Here's why. Now it's reproducible. The next person that comes to play with an XGBoost example can learn from this and maybe start where you left off, refining that parameter space, whatever it may be.
One of the things that you had in the notebook was your essentially your optimization budget, which looked like it was the number of trials you are afforded. How do you know how to set that? And are there other ways to set that in terms of, can you use more abstract metrics like a compute budget on AWS, for example, or something like that?
Yeah, so we provide guidance based off of the dimensionality of the parameter space, the types of parameters you're running, some of the advanced features that you might be using, like parallelism or multi-metric optimization. Loosely, though, it's linear with the dimensionality of the parameter space based off of large empirical studies that we've done. And what we end up seeing is, again, somewhere between 10 and 20 times the dimensionality of the parameter space is usually pretty good, especially for these simple machine learning algorithms. Okay. So we took something that would be 100,000 parameters in a grid search, and we've taken it down to 100 different parameters that we've tried here. But I'll show a quick example that might show just kind of the iterative nature a lot of our customers go through with our tool that will expand the number of parameters we end up needing to do. So let's say I looked at this experiment and I saw, okay, I got 65% accuracy. That's pretty good. But now my boss came and told me that the model's too big. It's not explainable enough. You have too many estimators. You need it to be smaller. And I say, well, you want it to be the best model possible, right? I got 65% at 74. And they're like, no, I want to understand how you make those trade-offs. So you could potentially just drop down here and get them the next lowest thing. But what SigOpt allows you to do is explicitly encode that into the search. So now we take the exact same experiment we had before, where we're tuning the same things. In this case, maybe we're going to delete call sample by tree because that didn't have very much effect on the end results as we saw from that analysis. Again, this was randomized data, so I wasn't sure which one might matter, which one might not matter.
Do you have to then explicitly set it to 1 or the starting place to 1, or is it that just going to be figured out somewhere?
Yeah, so XGBoost has default keyword args, and so it'll just go back to the default.
Got it.
And in this case, my observation budget, instead of being 5 dimensions times 20, I'm going to switch it down to 4 because we limited the size of the space. I am going to add this multiple of 3, though, because I'm not just going to be optimizing the softmax objective metric, but I'm also going to be minimizing the number of estimators. So I want SigOpt to make this efficient trade-off between these two things. Find me the best thing you can, but with the fewest possible estimators. And instead of getting a single answer, I'm going to want a Pareto frontier of these trade-offs. The rest of the code is identical. You're just giving it 2 values instead of 1. But this is very powerful in helping you make that business trade-off. And so what we'll do is we'll go ahead and kick this off. We did need to set it to 1. Back up here. This is the joy of live coding. Sam was correct. Sam, I'm going to have you do my code reviews from now on. Because while XGBoost allows it to happen.
I think that was the wrong place. You deleted it from the place that you needed to set it to 1.
All right, I'm just going to stop being clever and put it back in down here. We'll search over it anyway. All right. Because I'm pretty sure this should work because it's just a modification, again, of what we did before. So jumping back to our experiment dashboard here, we'll go back. We'll see that now that there are 2 experiments created, including this one that is not necessarily giving us that best seen trace as we saw before, but now it's giving us this Pareto frontier of trade-offs between the number of estimators. In this case, it found something with only a single estimator, getting us 0.525, as well as this one that got 65%, 65 estimators getting us 0.575. It's trying to optimize these two things simultaneously. And as we let this kind of run for a few more seconds, what we'll see is from the business use case, there's these trade-offs that you may be willing to make and other things that you might be willing to track. Like, I want to see how different depths and different learning rates affect these individual parameters that I'm caring about, and which ones lie along this Pareto frontier. I want to see for different individual metrics. Obviously, the number of estimators is a huge importance for the number of estimators metric, and it doesn't really matter for the others. Whereas min-child weight for this this multi-metric experiment ends up being the most important metric for the softmax. And as we let this run a little bit longer, as I said before, we multiplied by 3 to really show that instead of getting a single answer, what we want is this Pareto frontier of trade-offs. We're finding similar results to what we saw before, but allowing us to again say, how exactly do we want to make that trade-off between the size of the model, where we could get a micro model that actually does pretty well, or one that's 63 times larger and does a little bit better, really allowing us to make that trade-off. We see this happen all the time for more real-world examples between things like memory size, power consumption, inference time, versus a accuracy metric like log loss or whatever the actual business is. So it's a good thing you want to maximize and a bad thing you want to minimize, but you don't necessarily know what that trade-off is ahead of time and can't do a normalized composite objective function. You want to be able to say, I'm going to pick this one out and use that. And again, this is where that really matters, to have that system of record of experimentation, because you can say, tried this first on one metric, then I decided I wanted to minimize things, and then I selected this specific point. And again, it creates this trail for people to follow behind you if they want to do a similar problem that would otherwise be lost if you were cobbling together open source or brute forcing this or doing this manually. And you can see we're getting to the end of this one here. Took a few more minutes because we went up to 300 observations, but it did get us these interesting results where we got up to 60% accuracy with 11 estimators, back up to that 65% accuracy we saw before with 63 estimators, which was less than we had previously. And we can really then go back to our boss and say, okay, you wanted it to be smaller. How small is good enough? How much of a trade-off do you want to make? Apply that domain expertise and contextual awareness to select whatever point that you actually want to put into production, and be able to say, this is exactly what we're running with in the actual use case.
Nice. You mentioned being able to apply the same kind of process to not just the model parameters, but things like memory and power consumption and things like that. When you're doing that, where does that information come from? Is more complicated to expose those types of metrics to SigOpt?
No. So if you can calculate it, you can give it to SigOpt. So here we're getting the softmax.
How do you calculate power consumption, for example?
So you probably have some sort of simulator that allows you to see, or an emulator on a specific device, or you might know, given a specific power, a specific parameter set, there might be one evaluation metric that gives you accuracy and one that tells you memory footprint or power consumption or whatever it may be.
For power.
Exactly.
Got it. Okay.
What we find with a lot of our customers is there's usually not just one thing that they care about, but there's many things. There might be one thing like money that they really care about, but there's many things that they look at, many different trade-offs that they make. They might not just blindly go for that best possible academic metric, which again, certain more automated systems might do. And they're applying that domain expertise to make different trade-offs. And what SigOpt allows them to do is optimize multiple metrics, set thresholds on multiple metrics, really make sure that you're looking at this whole process holistically, gaining the insights you need to be able to decide what to do next, but have a system of record for doing it and have a powerful tool for being able to achieve those goals. And we're continuing to develop more and more tools in this space. This was multi-metric, but I hinted at others like thresholds, being able to store many metrics, and more that we're developing all the time.
Okay, cool. Neat. Is that are there any other parts to the demo?
So that's the live demo there. We do kind of go into more detail about some of those more advanced features, things that allow you to kind of extend this to different types of problems, whether it's deep learning systems where you might be able to track things as they go, problems where you might be able to break it into smaller chunks, problems where you might be able to leverage parallelism. We'll pass on some links to some of this, and we go much more detail in our blogs or blogs with our partners or some of the academic work that we publish at workshops at ICML, NeurIPS, and things like that. All of this is available at sigopt.com/research or sigopt.com/resources.
Cool. So what are the three, if you had to name three things that folks need to think about differently to kind of get most advantage of a tool like this, or I don't know if it extends generally to AutoML or other types of other aspects of the platform, AI platform stack. But how do folks need to change their thinking to take advantage of tools like this?
Great question. So there's really three areas where this can be applied.
You've got a slide for everything.
There's really three
You're
areas.
Going to make folks think I'm just like sitting here throwing you softballs, and that is not the case. Or maybe it is the case. It's not the intent.
No. So we've done this many times with many different firms. Many people who are familiar with the field, like yourself, ask very similar questions. I think a lot of what our customers get out of us actually is the expertise to help them with questions like you just asked. We've been doing applied real-world optimization and experimentation with some of the leading firms in the world for the better half of a decade now. So we can really help lay that foundation to make sure you're getting the most out of these tools, you're doing the best practices, in addition to having the very best possible tool for the problem. But where we see, to answer your question, three areas where people see the most application for this, it's when they're exploring different things. So it's in the R&D phase. It's about failing fast, learning fast, making sure when you try a new model, you pull some open source out of GitHub, or you're re-implementing a paper from NeurIPS or whatever it may be, that you're really getting the best version of that model, and you're doing that experimentation in a repeatable way, in a scalable way, and you're comparing the gold standard to gold standard. And this can really help when trying new things out, failing fast and learning fast. Mm-hmm. Scale is closer to that automation that you were talking about before, where we're plugging into larger platforms where maybe behind the scenes experimentation and optimization is happening. We see this across large credit card firms, streaming services, et cetera, where there's a tool in place to leverage large infrastructure, large data sets, and things like that. And this is just a way to get an extra order of magnitude or two savings from traditional experimentation approaches. So it's plugged in the background. It's about incremental performance across the board, kind of having this rising tide effect to the line of business metrics. And the final position, which is actually an area where a lot of people naturally go to when they think about experimentation optimization, is after they've applied all of they can in the data, in the model, in the computation, how do they squeeze out performance that would otherwise be left on the table? This is how a lot of the algorithmic trading firms use us. This is how some of the most advanced teams in the world use us. It's about saying, we've already invested so much, but we think we can get more. And it's that additive boost on performance that really drives value to them. So learning and failing fast at the beginning, scaling up to all the problems in the middle, and then taking your most sophisticated models and really making sure you get the most out of them. And we have lots of use cases with customers where they've saved a bunch of time across massive data science teams in that R&D phase. This one global technology consulting firm saved 30% for their client engagements that was otherwise wasted reinventing the wheel every time they had to do optimization. a large streaming service that we all know and love, being able to boost some of the platforms that go into training their massive models that go into their recommendation system, to firms like 2 Sigma with hundreds of brilliant quant researchers who are experts in their domain, tens of billions of dollars of assets under management, but it's about taking what they've built and providing this augmented additive boost on top of it to really get them the best possible performance. And we see this across the board for these extremely advanced teams.
Cool. Well, Scott, thanks so much for hanging out with me here and walking me through the demo. And this is going to be one of the very first TWIML Democasts. I hope it is a format that folks like. Definitely reach out and let me know, let Scott know what you thought. And I'm sure I'll see you soon, Scott.
Definitely, and thank you for the code review mid recording. I should have listened to you. Next time, I won't code something up that we're recording half an hour beforehand.
All righty.
Excellent. Thanks, Sam.